And yeah, like Alex said, this is the last seminar of our seminar series on tissue engineering and 3D bioprinting, and also last seminar of the year. And to end this seminar series, we're excited to have Dr. Lee here with us to talk about engineering biomaterials to mimic and repair tissues. So Dr. Lee is the Canada Research Chair in Biomaterials and Musculoskeletal Health. He is an assistant professor in the Department of Mechanical Engineering and also associate member in the Department of Biomedical Engineering and Surgery at McGill University. He graduated from Zhejiang University and obtained his PhD in mechanical engineering from Harvard. And he conducted postdoctoral research at Harvard Institute with one of the pioneer in the field, Dr. David Mooney. His current research focuses on the design and mechanics of biomaterials for tissue repairs. And Dr. Lee received numerous awards, which includes the Christopher Peer Research Excellence Award from McGill, the WIS Technology Development Award from Harvard, and he's also listed as the Innovators Under 35 by MIT Technology Review. So lots of prestigious awards here. Dr. Lee, we're very excited to have you today, and we look forward to your talk.
Okay, yeah, thank you so much. Thank you, Boyan, for the nice introduction, and also I'd like to thanks again for this opportunity. It's my honor and pleasure to present our work in this seminar series. And before I starting the content, so I'd like to acknowledge the contribution of my students, as well as a lot of great collaborators, including Professor David Mooney from Harvard. And I also like to acknowledge the funding support for those work, particularly including the NSERC and the FR20, the Quebec Provincial Funding Agency, and also the NIH from the US. Okay, so since that's the final webinar for this tissue engineering series, and I think everyone should be convinced that tremendous progress has been made in the tissue engineering, and nowadays, right, has different kind of approaches to engineer the cell, material, and also to fabricate the tissue architecture. And there must be a lot of great bioprinting work has been introduced, including I realized the previous webinar was provided by Frank Zhang from Harvard, and all those great work has contributed to the generation of very nice kind of artificial organ for the in vivo implantation, as well as like those in vitro model can use to model disease like organ on chips. And that is kind of the one big aspect for this tissue engineering paradigm is about the biofabrication. And for those artificial organs, eventually they would be implanted into the human body. And that would be kind of the late stage of those paradigm would be about the biointegration. And for today, my talk, I would like to highlight our work working on these two aspects. One is on biofabrication, bioprinting. Another one would be also be nice to present it at the end of this kind of webinar series about biointegration. Assuming at the end of the day, we have the great functional, perfectly artificial organ, but we need to integrate it with the human body. But that last step actually represents a lot of challenges. And to that aspect, I will introduce the biointegration technology developed from my lab. Okay, so first about this biofabrication. The bioprinting has enabled a lot of possibility to create those artificial organs, right? So some very famous work from like Frank Zhang's lab at Harvard, and also Feinberg's lab and Jennifer Lewis' lab from like the US. And nowadays we can fabricate nice scaffolds with defined structural and mechanical property and biochemical kind of property for to be used as this kind of artificial organ. And I just want to highlight a lot of success has been made to achieve those defined features at the macroscopic scale, as well as mesoscopic scale, such as the scale of the blood vessels. However, there's remain a key challenges at the smaller scale. Those would be the focus of my work that focus on the micro scale. In terms of micro scale, we need to define those microstructure and the mechanics kind of sense and feel by the cell incorporate inside in order to achieve the proper function. In that aspect, the mechanics of those environments are very, very important. So that would be, has been shown to regulating a lot of different behavior of cell, including like the stiffness of the matrix, including the viscoelasticity. So that essentially is to consider the fact a lot of biological tissue behave both like a solid as well as a liquid, right? Those kind of mechanical property has been shown very recently to show regulating the spreading, proliferation, and differentiation of different kind of cell. In terms of microstructures, a lot of organ and tissue will feature a very dedicated, very fine structure in the micro scale, right? A nice example here is this kind of areolar sac structure. You can see a lot of micro scale kind of little pockets to hold the air, enable this kind of air exchange. And again, this kind of mechanical environment of those tissue has been so important to regulating the activity of the cell. So the challenging here in general is like we need to really mimic not only the macroscopic property, but also the micropore structure of those native tissue, and not only the basic stiffness, but also this kind of like nonlinear and complex mechanics of the native tissue. Another big aspect I will talk about today is about biointegration, right? Just assuming at the end of the day, we have the amazing organs. So that kind of represent this challenging about biointegration. So far, in the clinic room is proceed by this kind of vascular suturing process. So essentially pioneered by the Nobel Prize winner, Alex Carrel in 1912. So that's a Nobel Prize in 1912. So that is mainly kind of about this technique to suturing the transplanted organs with the human body. In that case, this type of procedure called anastomosis is very, very important, right? So clearly success has been achieved, but the challenges remain, right? If you want to kind of really integrate those artificial, it can be from the human or can be artificial one from the tissue engineering approach with the native tissue. In many scenarios, it's not as simple as suturing the blood vessel together, right? So here, this kind of challenging has highlighted in this Science Review article, just said that unlike the bone, the cartilage regeneration remain a big challenging. And one of the primary challenges there is how you can integrate it, the artificial tissue engineered cartilage with the native cartilage. In that case, you need to not only integrate it, not only just implant this kind of material, but you need to ensure this kind of short-term and long-term integration between the tissue engineering material with the adjacent tissue, right? Adjacent cartilage, adjacent bone. But that has turned out to be very challenging. And that is the second kind of like focus for my talk today. Okay, so a further context about the challenging on the biointegration is highlighted here. As you can appreciate it, suturing procedure, it works, but it's not perfect, right? So it's mainly kind of point-wise integration between the tissue. In that case, you're using a stiff material that can causing like scar formation, inflammation locally inside the tissue. So here is a histology of a cartilage sample. And as you can appreciate, nearby the suture side, there are lower cell density and also forming this kind of micro crack inside the native tissue, right? So not only that, because it's point-wise fixation, it can have the leakage of the body fluids, the blood or the air from the lung. That's just like not perfect in terms of this kind of suturing technique. And stable is pretty similar. It involves a rigid material, it's non-degradable, and in that sense, it's worse than the degradable suture. It needs to be removed, kind of like involve secondary surgery. And to avoid those kind of like limitation, like people in the field has been working on, and nowadays we have different kind of commercial products, cyanoacrylate, super glue, used for the topical application, and that has been known to have a big toxicity effect, and is not generally recommended for use inside the human body. And the surgical glue is better in terms of biocompatibility, but they are very brittle. And if you carefully check those kind of very famous products from Baxter, according to the instruction, it's not recommended to use alone. It has to be used together with the suturing technique. Okay, so here we still need to improve this biointegration technology for the organ transplantation and for this tissue engineering material in order to integrate it with the human body. And for today's my talk, I would like to highlight recent work from my lab to address these two aspects of challenge. The first one is on the bioprinting, and we have some recent work try to enable us to mimic the microstructure of the biological tissue. And also the second part about the biointegration technology, we developed a bioadhesive with a very good, amazing mechanical property to enable this kind of very robust integration between the artificial material and the native tissues. Okay. Through my talk, you can also recognize I often talk about this kind of model material system. It's called Adhesion. So I just like to provide some kind of background about this type of biopolymer we often use in my lab. So that is derived from the stream shell. And initially it's in the form of chitin. As you can see, a lot of kind of acetate group. And after the acetylation process, this group can convert into a priming amine. And this priming amine will enable a lot of nice feature of this kind of biopolymer. So one of that is it carry positive charge in the neutral pH. And because of this, it can have the electrostatic interaction with itself, and it also can readily form the hydrogen bonds between kind of those hydrogen chain, right? In that sense, it can have this called self-cross-linking ability to form those reversible and physical crossing. As another consequence, it can have this kind of phase separation behavior to generating a nice architecture of the micropores inside the resulting matrix. So in addition to this physical crossing, it can also enable the covalent crossing. So for example, by simply do the carbon diimide chemistry, we can form the covalent crossing, the amide bonds between the hydrogen with like the secondary polymers such as alginate, or we can introduce the aldehyde chemistry, can cross-linking like hydrogen chain together to form a covalent crossing hydrogel. And here is an overview of the length scale involving in bioprinting and also biomaterial in general. And the macroscopic biomaterial containing a fine structure, right, in different scale. In the micro scale, we have the porous structure, which are needed in order to easy the mass transport. And also in the even smaller than scale on the nanometer, you have this called meshes of the polymer network, right? So those meshes provide the elasticity of the whole matrix. And here also kind of affecting the mass transport for those biomaterial. In terms of engineering, for the larger length scale, above like 1 micrometer, right? 3D bioprinting is appealing, and we can really nicely manipulate the structure on the order of at least like 100 micrometer nowadays. And then for the super small molecular level scale, right, it's mainly the job of chemists. We can do different kind of chemistry. And they leave a gap in the between, right? So those is the focus of our technology. We try to focus on those microscale pores on the order of 1 to 10 micrometer. And those are not easily kind of achieved by using the existing bioprinting technology because of the resolution. all because of the lengthy process, right? But they are very important in order to enable the mass transport. And unlike the small mesh, only allow the diffusion. In that length scale, on the micrometer scale, it can involve the convection to able to allow for a rapid mass transport at that length scale. And also, there are a lot of study to show those kind of opening are very critical to optimize the activity of some cell. And there are some reporting set like fibroblasts, they will prefer those kind of pore size of like around 10 micrometer as well as like a hepatocyte cell. And then, right, how to address this gap in terms of fabrication, how we kind of mimic those microstructure. The traditional approach involving like source leaching, involving the freeze drying. I think you may be familiar with many of you, right? So essentially you need to have the material, freeze it, and then you dry that to remove the water ice crystal to leave some kind of opening, right? So that is a very, very well documented. And the limitation for this approach is obvious, right? You cannot load the cell directly because if you load directly, you kill the cell. It's involved this kind of very extreme temperature and processing condition. And if you try to make a small pore, that's feasible. However, it's very difficult to seed in the cell, especially when you are targeted the pore size is on the order of like 1 to 10 micrometer. It's comparable to the cell. The cell will feel a tremendous amount of resistance to loading it that limits like the cell seeding density and also, right, so that would be limited function of those tissue engineering scaffold. So that is a recent progress has been done in the field, including the work from String John who presented last week, right? So that is called Micropro-Forming bioprinting. And the state of art involving to embed some of those templates. Those templates can be a small micelle, and those kind of microparticles can be leaching out, right, in a very mild condition, or just like some kind of oil phase can leaching out. So that is nice to create the micro scale pore. However, the limitation is following, right? In the case of the micelle, they are using this kind of spherical particle, and it will leading to a limited interconnectivity between those pores, right? So in that case, you won't have the rapid mass transport by convection throughout the whole matrix. And in terms of this kind of oil phase emulsions, you can create interconnected pores. However, the mechanical property often is a limitation because without engineering the mechanics, those matrices tend to be brittle because those pores are served as a defect, right? Those are defects are knocking out the mechanical strength of the whole matrix. And also in the state of art, people have limited ability to tune the mechanical property of those matrices. And often those are covalent crossing in terms of mechanical response, they are mainly elastic. So they may limit the activity of the cell. Okay, and in order to address this kind of challenge, like my student, Guangyu, so he proposed this called trigger micropro-forming bioprinting. So unlike the previous strategy to using those micro templates embedded inside the bioink. So what we do is like we introduce this called stimuli trigger phase separation mechanism. So it's a very, very fundamental mechanism in like material polymer science. By doing this, we can kind of spontaneously generating both polymer phase, solid phase, and also water phase inside the printing structure. So nicely, we can have this kind of opening space, which mainly water phase can provide those micropores living in the matrix. And because this stimulation we provided based on very mild conditions, such as sodium bicarbonate, just like slightly kind of like a base condition, including like body temperature around 37 degrees C. The combination of those stimulation together can enable us to spontaneously form those printed structure inside a supporting matrix. And I should note that this supporting matrix we use a gelatin slurry, and after the printing, and we can easily remove the gelatin slurry as like this called fresh bioprinting, kind of pioneered by the people from CMU. Okay, and not only enable this kind of printing process, with the material system we use, which is Hydrogel, allowed us to further tune the mechanical property of the matrix. So because the Hydrogel can readily form these physical interactions. So those physical interactions can be interfered or can be controlled by a secondary species such as PEG, which also can able to form some degree of the hydrogen bonds. So by adding this kind of PEG polymer, and we can tuning the relaxation behavior of those matrices, and things the cross-linking is based on these hydrogen bonds. By tuning the pH, and we can readily tune the storage modules, the stiffness of the whole matrix over a wide range, just like according to, depend on the very small change of the pH. Okay, and nicely by having this system, and we can achieve similar mechanical response with the biological tissues. So here, what I want to emphasize is not only the stiffness, we also capture this whole scale of time-dependent relaxation behavior, as I show this comparison with different kinds of tissue, like adipose, liver, brain, or like bone marrow. Okay. And here we characterize this microstructure of the printed structure. So the result indicate this phase separation mechanism to work, and we can create it this kind of highly interconnected micropores resulted by this phase separation process. And in comparison to this kind of nanoporous or non-porous hydrogen hydrogel, right? You don't see this kind of phase separation behavior in comparison. And this structure can be seen in the SEM, and because it providing an opening space for the cell to migrate, to proliferate, and we observe a much higher cell mobility inside this kind of microporous matrix. And the polymer itself and also the gelation condition is pretty mild, and we record a very high viability. So that's the comparison here compared to the nanoporous hydrogel for the Hydrogel, because it involves like aldehyde chemistry, and it tend to knock down the viability of the cell within this kind of control condition. And because we have this kind of highly interconnected pores, we enable a rapid and effective mass transport over a large scale. So here we just demo that by fabricating these specimens of like 6 millimeter, that's pretty microscopic scaffold, and we can have this matrix just relying on the passive transport of the nutrient, and we can have this matrix to supporting the full viability of the cell throughout this 6 millimeter length scale. So in comparison, if we use a nanoporous gel, and you only can supporting the cell viability close to the surface, but not the core of this printed material. And this material system has been demonstrated to develop this kind of in vitro model to study the vocal fold regeneration. And in that case, we show that we can print it with the fibroblasts for the vocal fold, and we can seeding this endothelial cell on top. And we can see that in terms of this kind of opening porous structure, it enables the spreading and migration of those fibroblast cells, and we observe a much lower circularity compared to the non-porous hydrogel. In the study of the cancer cell culture, we again compare to the non-porous gel. By having our porous matrix, we enable the proliferation of those cancer cells, and also by comparing kind of different viscoelastic property of those matrices, we also recording like this kind of very nice dependence on the viscoactivity of matrix. So that consistent with the previous work done by from the Mooney lab at Harvard, just showing that the more viscoelastic matrix kind of promoting further the proliferation and spreading of those cancer cells. So here, just a brief summary of this work. We show that right? By introducing this phase separation behavior into the bioink, we can fill the gap in the field of bioprinting. So we can make this kind of porous viscoelastic matrix to have this cell size pores and also to have a very wide range of tunable viscoelasticity. So which is not possible by using previous technology. Okay, and throughout this study, and we also recognize the limitations of this material system, and particularly is the mechanical property of this physical crossing matrix is not sufficient. So the following work we just recently released online in Advanced Science is to use a double network strategy to reinforce the mechanical property of those hydrogels. So the strategy we took is pretty simple. We just have introduce a secondary polymer network into the hydrogen matrix. So this secondary network is crossing using the aldehyde chemistry. So by introducing this double network designs, we can very effectively toughen the hydrogel. Just to show that by using these hybrid designs, we can raise the toughness from initially pretty brittle matrix to like 40 or 50 joule per meter square, and also has a higher stretchability. So that is work again done by Guangyu and also another student, Sarah. So they also show that by introducing this secondary crossing, we can manipulate the pore size and the porosity inside the hydrogel scaffolds. So just to show that, right, by introducing more covalent crossing, and we can lower down the pore size, and also it also has a consequence to lower down the porosity inside the matrix. So with this, we want to further benchmark how about the permeability of those hydrogel. How does this hybrid crossing design affecting the mass transport? So here we do build up these setups to measure the permeability of the nutrients throughout this hydrogel matrix. And what we can recording how's the pressure change and also the flow of the media. And we can calculate the permeability of this matrix, and by further compare with the existing hydrogel system. So we reported our porous, interconnected porous network has a 4 to like 2 order magnitude higher permeability compared to like nanoporous like PEG hydrogel or gelatin hydrogel. And that is comparable to some kind of porous tissue such as foam. And this material system in general has a good cytocompatibility. And also this pore size shows similar kind of ability to supporting the spreading of the cell encapsulated inside. And to further test the application of this kind of double network systems, so we use it as an injectable hydrogel system. And here we demonstrated it can be used in a microfluidic device. We can inject this hydrogel into those channels, and as compared to the nanoporous or non-porous hydrogel, which cannot be perfusable, our porous hydrogel is easily can enable the direct media perfusion. And that they will enable like the viability of those cells throughout this kind of whole channel. So here this channel is like around 10 millimeters in size. And this kind of like material and system can be easily kind of injected into multiple channels. And since the permeability is so high, and we can even connect the multiple channels together to enable like a larger perfusion system. And to further demonstrate these benefits of the mechanical property, so we work for this work with Professor Lux Mongzhu and McGill, a very nice colleague, and they have developed this kind of bioreactor system to mimic the phono process, basically the airflow of the vocal fold. So here with this kind of vocal fold bioreactor, so we inject this kind of like hydrogel into the channel embedded in this PDMS vocal fold-like device. And here is a video to show how this bioreactor works, and that is function in the normal speed. As you can appreciate, is super high frequency of the mechanical stimulation. It's around 120 hertz. And also we kind of stimulate that for a long time. So throughout the whole test, we apply more than 6 million cycles of those kind of vibration. And surprising, we found our kind of double network system can survive those extreme mechanical stimulation. So without breaking, and the covalent crossing non-porous hydrogel are break into like small pieces and wash out by the media. It cannot be found. And also this kind of like single network system has a lower toughness and it fracture into like different pieces after this kind of mechanical stimulation. And we further show that this mechanical stimulation is beneficial to promoting the activity of the cell, to show that with the formation and the cell tend to deposit more collagen, as you can appreciate from this confocal imaging. Okay, so just switch the gear a little bit about the bio-integration technology. So we have introduced, right, the suturing technique is the gold standard to integrate the tissue engineering or transplanted organ with the human. But they are not perfect. It has a much higher mechanical stiffness compared to the native tissue. Just to show in this, a lot of soft tissue has a much lower stiffness in comparison. To this end, the hydrogel are amazing because it's very soft, it's very hydrated. However, when it comes to this biointegration application, hydrogel has significant limitation. It is not adhesive, right? So here, hydrogel has been developed for the bioadhesive application for a long time. And I want to introduce you this brief history I prepared for this kind of bioadhesive technology, starting from this kind of fibrin, Nogen and fibrin glue-based hydrogel to some recent work and we have working on, and also some other very famous work like those muscle-inspired adhesive people have worked in the past decades. And it certainly is a big market size. And throughout those studies, the tough bioadhesion remaining challenging to form. So why is that? Like hydrogel is not adhesive because it's mainly content of water. In my lab, we have tried to quantify this adhesion performance by using the fracture mechanics approach. So here we quantify the adhesion by using a parameter I like to introduce called adhesion energy. So essentially that is the mechanical work, mechanical energy you need to do in order to peel unit area of those adhesive from a substrate. So for the hydrogel case, without proper design, without any adhesion function, the adhesion energy is on the order of 1 Joule per square. So that is comparable to the surface energy of water. In terms of the native bioadhesive, which is blood clot, it has a pretty weak adhesion. So we measure the adhesion of blood clots recently is only on the order of 1 to 10, and is comparable to the surgical glue. But both are order of magnitude lower than those adhesion presented by the biological tissue, such as the cartilage here with a bone with around 1,000 Joule per square. So how we can kind of fill this gap? So that is the focus of my second part of the talk about this biointegration technology. In order to answer this question, right, I would like to provide a background why bioadhesion is challenging. So there's a recent review by my student, and we just want to highlight in terms of bioadhesion, it dealing with biological tissue. Biological tissue has a wet surface and have very complex chemistry and architecture. And in terms of the mechanical property, it exhibits a diverse mechanical property. It can be very viscoelastic, it can be super tough, or it can be super soft. And not only that, it's subject to very complex mechanical loading by the environment or by itself, right? In the case of cartilage, is subject to like on the order of 10 megapascal of stress during the function. And how to form those bioadhesions or what it matters. So here is a governing equation underlying this mechanics problem. So essentially those adhesion energy has 3 contributions, right? It contributed from the interfacial bonding, another contribution from the tissue substrates and also the adhesive matrix. And then, in order to develop a better bioadhesion, bioadhesive system, and that's visit the fundamental of all those three contributions. The first one is very well appreciated. It's about interfacial bonding. The interfacial bonding involve the chemical reactions, right on the surface to bond the adhesive with the tissue, right? So here we have developed a big library of chemistry in the field. But all of that, essentially, you can see based on the carbon-carbon bond or nitrogen-carbon bonds. And what's their contribution and what's their physical limits to this gamma zero intrinsic work of adhesion? It can be estimated by using the Lake Thomas model. Essentially, the total amount of those energy depends on how many kind of polymer chain you need to break on the surface. By input those representative number, we got the gamma zero is on the order of 10 joule per meter square. No matter what kind of chemistry you use, that is the physical limit. And then, what's the second contribution? So from the tissue, the picture is much more complicated, right? Tissue is very complex mechanics response, and also this kind of pitting process involve a very highly nonlinear large deformation mechanics. To do that, our students have done this kind of holistic finite element simulation to consider different kind of mechanics of the tissue. We tested skin, liver, and the blood vessel, and we considering the typical mechanics of the hydrogels. And together, we found that because of the stiffening effect of the tissue, it contributes negligible to the adhesion energy. So at the end of the day, what you have the adhesion energy is mainly dependent on interfacial bonding and adhesive matrix. So in terms of the adhesive matrix, so that is the limitation for the commercial available product. They tend to use a very simple hydrogel system. The single network hydrogel are brittle hydrogels. So the toughness of those hydrogel is general, again, on the order of 10. So you will end up with the total adhesion energy is on that same scale. So which is much lower than what you expect to get. So how we can achieve a better performance? We don't have much space to tune in terms of gamma zero. The real space is to tune this contribution from the adhesive matrix. So that is a pure numerical study. By having the matrix can dissipate more energy, and we can easily raise up to reinforce the adhesion performance. So that is the design strategy, and that's why we call our adhesive is tough adhesives. So that is a demonstration of the adhesion and also the stretchability of our system. It can stretch it to large stretch ratio, and how to enable that. That's come to the design. The design is try to optimize the two contribution, right? We need to optimize the intrinsic adhesion by having a strong interfacial bond with the interface. So in this case, we use a hydrogen, which can have this amine bond formation and also can have electrostatic interaction with often negatively charged tissue surface. And then in terms of matrix, we use a very tough hydrogel based on the alginate and polyacrylamide hydrogel. I don't have time to go into the toughening mechanism, but the nice thing what we have demonstrated in our previous work is we can enhance the toughness of this hydrogel to a level comparable to the natural rubber or elastomer used in a car tire. So like on the order of 10 joule per meter square. The combination of this enable our design, and we can have both large contribution of the interfacial bonding and also adhesive matrix. And adhesive matrix is dominant, right? It's on the order of 10 joule per meter square, and we can end up with a much higher adhesion energy compared to the intrinsic work of adhesion. So that is nicely demonstrated, and we measure this, confirm that by performing pitting tests, and we have a much higher adhesion energy compared to the super glue, which is known as the strongest tissue adhesive, and also much better than the other kind of adhesive under development, including nanoparticle and also muscle-inspired adhesives. And that is just a comparison to make this point. We need to have both the good interfacial bonding and also a good tough matrix in order to have their good high summation to get a high adhesion energy. And our system is outperformant like the state of art of those bioadhesive and is comparable to the cartilage, which has a good tough adhesion with the bone. And then because of the chemistry used is working or focus on the general tissue surface property. And we demonstrated our strategy work on different kind of tissue, and they are consistently outperforming the fibrin glue used in the clinic. And since it is water compatible material and water compatible chemistry, and we has independent kind of performance of the blood exposure. The cyanoacrylate, the super glue, in the contrast, we have a much worse performance because the blood, right, it kind of triggered the instantaneous solidification of the cyanoacrylate. In that case, it cannot form adhesion with the tissue. So just like a brief kind of proof of concept, we use this kind of beating heart model to show that a blood exposed surface, and then we can apply our tough adhesive, and then within 1 or 2 minutes, and it can form a strong and tough adhesion on this kind of beating hard surface. So let's just like a video to show in this region, we receive the compression, so we form the adhesion, and it is sustain the large deformation and pitting stress. Okay, so that just like highlight a future. We can have this to maybe to replace some of the suture used for the soft tissue. Okay, and there are some recent work also from the Mooney lab where I conducted this adhesive work. And nowadays we can also by design a degradable hydrogel matrix, we can have this adhesive to be removable and also degradable. And recently the related patent has been licensed to a company which is focused on the oral surgery, as well as many other applications we are pursuing in my lab and also at Harvard. Okay, so well, how much time I have? Is okay?
5 to 10 minutes. No problem.
Okay, yeah. So that is the final piece I just want to show you. Is want to take a step back, right? I just highlighted in terms of biointegration technology, this hydrogel-based system is appealing. However, it won't kind of replace completely the suturing process, right? The reason is pretty obvious. Hydrogel are made of soft material, right? In terms of the strength, it's not comparable with the suture. So in that case, suture is still considered, right, indispensable in a near future. And also it has been widely used in the surgical setting. But in terms of the suture, it also has an even longer kind of like a development history since like Egypt times. And that is the last piece of work I want to highlight today is how we can find a good middle ground between this kind of surgical suture and also this adhesive hydrogel we have developed. And this middle ground is found by my student John Wei, and that is justified on the facts try to mitigate some limitation of the suture, including the mismatch with the soft tissue because it's too stiff. And I will show you our strategy can mitigate that limitation, and also it can causing some kind of like scratching friction with soft tissue. And all of that can be nicely kind of addressed by simply putting a very thin coating of those kind of tough adhesive on top of suture. So that's what we have done. And they is nicely demonstrated not only for like the PRGA suture, but as well as other type of suture, including the plain gut, essentially a collagen-based suture, and also like the non-degradable suture such as nylon. And this kind of interface between the hydrogel and the suture is super tough and robust. It can sustain the knocking process during the suturing process. And that is the benefit we bring by have this core shell designs of the hydrogel on top of suture. We won't interfere with the key feature of suture. That is the strength. So the modified suture maintaining a super high tensile strength, and our material in turn can lower down significantly the surface stiffness of those suture. So here can reduce it from like 70 megapascal to 7 kilopascal. And having this hydrogel surface we have enabled this lubrication property, and they can significantly reduce the friction coefficient of the suture on the tested PDMS surface. And then it's because of this kind of like nice interface with the native tissue, and we also demonstrated in the in vivo study, we have this coated suture. It just induce very minimal inflammation, and we all found that during the long term has even better kind of like biocompatibility with the pristine suture from Johnson & Johnson. So that's tested is the PLGA one. And this kind of like coating doesn't interfere with this kind of normal application of suture. We demonstrated we can also use this, we call it TGS suture for this wound closure application. And we don't see kind of inflammation or immune response adjacent to the suturing sites. So with this kind of like a hydrogel platforms, it allowed us to do many different functionality with the suture. So here, what we proved first, by using this hydrogel, we can enable the better antibacterial function. It not only prevents the adhesion of bacteria, but also by encapsulating these antibacterial agents such as BZK, we can activate killing those bacteria which may happen to stay on the suture surface or adjacent tissue sites. And with this kind of the hydrogel coating, we can also incorporate not only the drug, but we can incorporate the microparticle and nanoparticle. So for those microparticles, we use a pH sensing bead. We show that this suture enable some pH sensing performance. So basically depend on the pH of the wound sites, and you can respond by exhibit a different color. Not only on the topical application, we further show that by incorporated with some functional nanoparticles, we enable this bioimaging function with the suture. So here we incorporate a silica-loaded fluorescent particle, which emitting near-infrared lights in the near-infrared window. So in this case, we can see this kind of signals from the suture can even penetrate through the tissue and enable this kind of bioimaging performance. So that's the last slides of my talk. So I just want to kind of highlight to you about the work currently going on in my lab. We are advancing both the science technology and try to better mimic and also repair tissue. And that is the research doing in my lab is highly interdisciplinary. We focus both on the material and the mechanics, and then we try to explore kind of different kind of biomedical application. And we have opening, and particularly I'm looking for the student and postdoc working in the orthopedic area, such as intervertebral disc repair. And also we have an ongoing project focused on the hemostasis and the blood clotting biomechanics. And if you have interest, so don't hesitate to contact me. So that's all for today. Yeah.
Thank you, Jenny. Thanks for the wonderful talk. Yeah, this is amazing work that shows how you can really push the boundary of what you can do using a hydrogel, right? From porosity to mechanical strength to adhesion. Very cool.
Thank you.
Any questions from the audience? Alex?
Okay, thanks very much for the really nice talk. I have a number of questions, but I wanted to start with the sutures that you showed that you coated with the hydrogel. So I didn't quite get how you do that. So how do you take the suture and coat it uniformly with the hydrogel?
Okay.
What's there?
Yeah, so great question. So due to time limit, I don't go to the detail, but it's you can appreciate it vary from the type of suture we are doing. And the essential idea is similar to this top adhesive story. We need to have a top hydrogel in the first place, and then we need to engineer the good bonding in the between. So in the case of plain gut, which is collagen, we can simply use the strategy we have developed before for the bioadhesive by attaching those hydrogel onto the plain gut suture. In the case of the PLGA, because we need to expose some functional group on the PLGA surface. So here, what my student we have optimized is optimize the sodium hydroxide condition to treat with PLGA to expose some of the carboxylate group on the surface, and then enable this kind of like simple carbon diamide chemistry to bond in with the top hydrogel coating. Yeah.
So do you just, mix in the suture with your hydrogel precursor and then it forms and you pull out the thread, or do you have to pass it through somehow?
Yes. So in terms of the detailed fabrication, right? So I just introduced the chemistry, and in terms of fabrication, it can be kind of reacted in a defined kind of like a capillary tube to define the real thickness we want to achieve. They can really tune the thickness, or we can kind of pull in the suture using kind of dipping method. But in that case, we have kind of less controllability of the thickness. It's not as confined as this capillary tube approach. Yeah.
Okay, thank you. That makes sense.
Any other questions from the audience? Maybe I will ask a question. So I actually have a question on the porous hydrogel work.
Yeah.
That we talked about. The base material for this hydrogel is PEG, right? So you're
the porous the essential material is chitosan.
Okay.
Yeah.
Okay. So yeah, and okay. So with chitosan, if I understand it correctly, you're cross-linking chitosan first, like the hydrogel is formed or cross-linked first, and then after that, you raise the temperature to change the phase of gelatin and then to introduce the pore. Is that correct?
Yeah. So here we are on those slides. I can kind of better describe this process. And sorry, kind of it's not very clear due to the time. So essentially, the physical process happening is following. You extruded this chitosan in this kind of gelatin slurry supporting matrix, and you have this triggering agent, which are bicarbonate, sodium bicarbonate, will diffuse into the extruded chitosan, and then they can inducing a phase separation. So essentially, they kind of like will taking out some of the primary amine, taking out some of the charge on the primary amine, kind of inducing the phase separation. So that is the first step, and then we'll move it to the higher temperature, and that will further reinforce the matrix, and also kind of remove the gelatin supporting matrix at the same time.
Okay, got it. Okay.
So here, yeah. So the gelation is kind of two-step process. The first one is based on the pH trigger, and also you can further reinforce by using the temperature. Yeah.
Okay. So the phase separation sort of happens first, and then you have cross-linking, right? Okay, that makes sense.
Yeah.
So I'm wondering, you compared the porosity of this material with gelatin, a few other hydrogels. I wonder, how does this compare with natural materials like collagen or fibrin?
Yes, so that's a great question. In terms of the collagen, it's a fibrous gel, and it has this kind of like micrometer pore size. So in that case, we don't include it. We happen not to include it in this plot, but I would expect the permeability will also high for the collagen because they are based on the microfiber from this kind of. They still have this kind of micro scale, but it's smaller. It's smaller compared to the pore size of our material. I think, but in that case, they all enable this kind of convection of the water instead of diffusion. And right, so what we're including here, including the PGDA, including the gelatin and the agarose, those are all has a nanometer scale pore. They're super small. in that case, the only diffusion allowed, so the permeability is much lower.
Mm-hmm.
Yeah. Mm.
Thanks. Yeah, the reason I ask is because for most biological experiment, we tend to use collagen fiber matrix, and in those hydrogel, we do see cells able to migrate, move around.
Yes.
So I imagine the pore size in those matrix will also be quite large too.
Yes, but yeah, so that certainly there's a nice benefit for this collagen gel, but in terms of their mechanical property, and it has been kind of appreciated, it's relatively kind of weak and soft in comparison. So yeah.
Great.
Thank you.
Any other questions? Okay, sounds good. If not, let's all thanks Dr. Lee. Thank you so much for the wonderful talk, and yeah, well, hopefully we can invite you back again in person in the future.
Yeah, thank you. Thank you so much for this opportunity, and thank you, Boyan. Thank you, Alex. Thank you.
Thanks very much for the great talk. That was great.
Yeah. Thank you.
Have a nice day, everyone.
Yeah, have a nice weekend.